Assalamualaikum and a very good morning to our respected lecturer. I am Dr. Faiz bin Aris and to all fellow classmates. Today, we will be presenting our project title, which is D flip-flop using Cmos technology in Cadence Virtuoso. This project was carried out as part of the BERG 4253 course, IC Design and Process. My name is Norfa Nabiti Fauzi, and together with me are Nofitria binti Salmi, Tan Jasrin, and Ho Jia Eng. We will walk you through the complete design process of a D flip-flop circuit, starting from its concept, going through the seamless implementation, and finally the simulation result and analysis using Cadence Virtuoso. So this is our table of content, which is introduction, methodology, Cadence Virtuoso workflow, schematic and layout, simulation waveform, and advantages and also disadvantages. And lastly is our conclusion. So let's begin with a brief introduction to the D flip-flop. A flip-flop is a basic digital memory circuit. It can store one bit of information and it has two stable states among various types of flip-flops. The D flip-flop, also known as the data or delay flip-flop, is the most commonly used in sequential logic designs. What makes the D flip-flop special is that it captures the value of the input D only at the edge of a clock signal, typically the rising edge. The value is then stored and sent to the output queue, regardless of how D changes afterward. This edge-triggered nature makes the D flip-flop very reliable in synchronizing signals, especially in digital systems like register, processor, and memory devices. Unlike latches, which are level-triggered, flip-flops only respond at a specific clock edge, making them more predictable. As shown in the diagram here, this is the basic structure of a D flip-flop, which includes logic gates configured to allow stable data storage based on clock transition. For the methodology, we choose to implement our D flip-flops using Cmos technology, and we design and simulate the circuit using Cadence Virtuoso, which is one of the leading software platforms for IC designs. In our project, we focus on designing a TSPC-based D flip-flop, which stands for True Single Phase Clock. This type of flip-flop is highly efficient because it uses a single phase clock and fewer transistors, which help minimize power and layout area. As shown in figure, our design uses just 5 transistors, 3 NMOS and 2 PMOS. This compact structure reduces not only power consumption, but also the propagation delay and chip area, which are all crucial in modern VLSI circuit. The TSPC flip-flop is designed to avoid clock skew issues and is well suited for high performance and low power application. That's all from me. And I will pass to the Hojia Eng.
Here is the Cadence Virtuoso workflow that we use in our design process. First, we start the schematic design where we create the transient level schematic for our circuit. Next, we perform transient simulation to test timing behavior, especially important for verifying the flip-flop operations. After that, we move into layout design, where we perform floor planning and generate the physical layout using mental layers and active regions. Finally, we conduct the design rule checks or DRC to ensure that our layout complete with the foundry design rule. In addition, Candace also provides tools for LVS, layout various schematic, and PEX parasitic extraction to further validate our designs. Here, we can see the actual schematic and layout generated in Candace. On the right-hand side is our schematic design. It shows the full transient level circuit for CMOS D flip-flops. On the left-hand side, the layout design, where the physical implementation is complete. We can also see that our design passed the DRC check, confirming that no design rule violations were found. The schematic implements a Cmos-based D flip-flop using TSPC logics. The transient connection ensures proper functioning based on D and clock input. The layout shows the physical design ready for fabrication using multiple metal layers, vias, and carefully placed active region to minimize parasites. Finally, passing the DRC confirms that our design complies with foundry manufacturing rules and is manufacturable.
Next, I'll be presenting on the simulation waveform. As you can see that our simulation result have three important variables, which are clock, D output, the D in, and our waveform output. The figure shows the transient waveform from simulation, clock, D input, and Q output. And the flip-flop captures the data on the rising edge of clock, proof of correct edge-triggered operation. Even if D changes in between the clock cycles, Q's only updates at the clock edge. The waveform confirms setup and hold time constraints are met and our output transitions are clean with no metastability or glitches. Next, I'll be presenting on the advantages and limitations. So there are four advantages that uh, can be seen from the D flip-flop simulation circuit. First is the simplicity with only one input of D and one output. Moreover, it is ideal for registers, memory, elements, and control logic. Third is to eliminate race conditions and invalid states, unlike SR flip-flop. While the fourth advantage is when implemented with CMOS technology or GDI DSTC, it offers low power output, compact layout, and faster response. While the limitations of this D flip-flop also be involved with no built-in toggle function, and this may encounter of not suitable for counters. Second is dependent on clock quality, sensitive to clock skew and jitter, while the last limitation adds a propagation delay which needs to put in consideration in high-speed circuits. In the conclusion of our assignment project with D flip-flop CMOS technology, the CMOS D flip-flop using TSPC logic is simple and efficient, and it is suitable for most digital systems. The simulation verified correct logical and temporal behavior, and the CMOS is important because it is reliable, robust, suitable for general purpose use. While the GDI and DSDC is for power, for low power or high speed needs. Lastly, it can be concluded that our design simulations pass all simulations and DRC stages, confirming the flip-flop is ready for physical implementation. Thank you.
As you can see here, this is the circuit that we have been made on the Virtuoso schematic editor N, and it consists of 2 PMOS 1 volt and 3 NMOS 1 volt from 30 flip-flop. So, we will launch ADEN for the simulation output. Using the transient analysis, we will conduct for the 160 nanosecond, and the output that will be plugged from the circuit is the clock, the D input, and the output from the circuit. After we make sure it's been plugged, we will save and run the simulation. In this simulation, we can see that when the clock is 1, the T is 0, the output will be 0. And when the clock return to 1 back, the T is 1, the output will be 1 again. This shows that the output from this circuit is the same with the D flip-flop table. Next, after we done the circuit simulation, we will go to the layout of the circuit. As you can see here, the component for the circuit already been there. So we just need to connect the part. So we'll be using 10 display label because we don't know how much path we will use. And the green and blue is the path that we have been connected. The blue is one label and the green is another label. It's already been connected to the pin that is the white box. After we done the design of the layout, we will make sure to run the design rule check because we want to make sure there has no problem in the layout design we have made. It was to avoid the short circuit in the design layout. Okay. As you can see, there have been no error we found in this, so this layout can be used for the flip-flop circuit. Okay, that is it for the simulation. Thank you.